and I understand why they do it, but I also don't like it.
Right, and we are allowed to disagree with our mathematical history. We just have to suck it up and move it. You have a section for me, please.
Darn those philosophers. Yep.
Yep.
Okay. Moving on to the next.
Chapter 5, sections 1 and 2 together. I'd like to answer this question. What is the sum of the first n odd numbers? But before I address this question directly, let me ask you a more general question. What's the difference between inductive reasoning and deductive reasoning? So I'm deducing from a set of properties, I'm deducing some rules. So what's inductive reasoning?
You put something into and then.
Kind of. But the idea is the reverse process. So I don't know the general rule. When I deduce, I take from those general rules and I deduce specific things. I'm going to start with a bunch of specific examples and see if I can induce an overarching rule. So I'm going to start to answer this question inductively. Means I want to look for a pattern. Before I can answer this question, I have no idea where to start. I just want to know what's the total of the first however many odd numbers. There's no rule given here. There's no thing for me to prove. But I can see if there's a pattern for me to find. So, first odd number is just 1. It's 1. 1 and 3, 1, 3, 5, 1, 3, 5, 7. Write out some sums. Give me some answers. What are the first? Do some examples. Let's see if we can find a pattern. Need to find out where the opera's coming from. What do you get? I mean, if I just add up the first one, I get 1. Hey, wait a minute. What do you notice about all those totals on the right-hand side? And not just any squares. This was the first 2 odd numbers, and that's 2 squared. This was the first 3 odd numbers, and that's 3 squared. That's the first 4 odd numbers, that's 4 squared. So if this total is the first n odd numbers, what's a pattern I think should work? Square what? And aha. I don't know how to write a direct proof for this. I don't know how to write a proof by contraposition, an indirect proof. I don't know how to write a proof by contradiction for this. I don't have a proof by cases. I can't just say, look, and so on, and hope for the best, because that ain't gonna prove anything. I need a new method of proof to try and figure out how to prove this. And the method I am going to use is an inductive argument. It depends on the ability to go from one number to the next. There are really two steps to a proof by induction. But I want you to think of it like climbing a ladder. In order to climb a ladder, you need to be able to get on the ladder in the first place, right? And then you need to be able to be standing on one step and get to the next one. I want to do those two proofs. I want to prove this is true for some starting point, a base case. The base case is basically pick a number, show your idea works. The goal is to pick as small a number as we can. Well, I already know it works when we pick one, right? So I've already done the base case. Matter of fact, I've done several versions of the base case up here. So I have a base case done. The second part is the inductive case. Now, in this case, we're going to do an if-then. Suppose it's true for some value. Okay. Use that to show it's true for the next one. From the floor, I can get on the ladder somewhere. And from any given step, I can get to the next one. The other commonly used imagery here is dominoes. You've seen those patterns when you knock all the dominoes over, they fall, and you make all these gorgeous pictures. Yeah, I'm setting up the dominoes. The base case is I can knock over the first domino. The induction case is that each domino will knock over the next one in the line. So, writing a proof by induction means first I have to have a pattern, something I hope is going to be true, and I'm going to give that a name. In our case, we're going to call that a propositional function. I'm going to call that P of n. Now my goal is to show P of n is true for all the n's I can show. So I pick the smallest value I think will work. Now, since we're counting odd numbers here, I'm going to assume that n is bigger than or equal to 1. Doesn't make sense to count 0 odd numbers. So here's my base case. Is P of 1 true? Can you answer that? Well, sure. If I plug in 1 on this side, the sum I equals 1 to 1 of 2i minus 1 is 2 times 1 minus 1, that's 1. And the right-hand side, 1 squared, is also equal to 1. Hey, those match. Yay. P of 1 is true. So that's my base case. To do my induction case, I need to write the if-then. So our induction case is going to look like that. From the K statement, can I get the K plus 1 statement? That means there's a hypothesis on the left side here. I need to write that down. I always write down my induction hypothesis. Now, I wrote it out 2 different ways. I wrote, hey, just suppose P of K is true. But then I wrote what that means. I knew I figured out that when I saw that the front table had no chairs. Well, please enjoy. Without this hypothesis, I'm going to have a problem. I won't be able to figure out how to get to the next one. So now I need to start looking at P of K plus 1. I'm going to do this as a direct proof. Can I use this statement somewhere to show what? Well, I want to show that. Somewhere in the midst of all of this, I'm going to have to see this thing. So let me start on one side of that thing I want to show. Which is the uglier of those two sides, the left or the right? I'm pretty sure it's the left side. I'm adding up all this garbage, right? So let me look at the left-hand side. And now I say to myself, how can I rewrite that to make it look nicer?
Separate it out, so we have sigma just up to K, and then we just add in the extra K plus 1 K to the end.
This says go all the way from the first to the K plus first odd number. What if I stopped one short? Then I would be saying, oh, really? Oh, wait a minute. Helps if I copy correctly. Have all of you caught the mistake I've made so far 3 times? I'll write it down. Ready? What's the mistake I made? Sign error. Minus sign. Minus sign. There. Which means that should end with 2 k plus 1 minus 1. Because this is what I get when I put in k plus 1. I did all the k, and then I did this extra one. By the way, if this bothers you, you don't have to split it off like the sigma. Remember that this is shorthand for writing them all out, isn't it? So you could write them all out. You just have to go to the next number. Seth, why am I happy to see this?
No, because we can assume that left-hand side is k squared. You can assume that the sigma of the k, 2i minus 1 is equal to k squared.
Again. So the goal is to keep in mind, the goal is to end here. So let me do a little algebra here. Multiply out that 2. Plus 2 minus 1 is k squared plus 2k plus 1. Hey, wait a minute. Back to that. That means I automatically know, because I've already proved this by hand. I wrote out the calculus for the 5th. Since I know the 5th, I know the 6th. Since I know 6, I know 7. Since I know 7, I know 8, 8, 9, 9. I can keep going forever, right? This statement is now true for every non-negative integer n. So my pattern actually does hold, not just occasionally. It doesn't eventually break. It holds for all values of n bigger than or equal to 1. Who's in Calc 1 this semester? Where are you in Calc 1 right now? Just started antiderivatives. Which means one of the things you're going to prove, or at least use, is the idea of adding up a bunch of numbers. We've seen this before. If I start at 1 and I start adding, we know what this adds up to. We did this before. We saw it as a pattern. but we didn't really prove it. We just kind of observed, hey, I can pair up the one at the front with the n at the back, I get n plus one. I can pair up the 2 with the n minus 1, I get n plus 1. And I end up with n over 2 pairs, each valued at n plus 1. So I get n times n plus 1 over 2. But technically, that's not a proof. That's the way Gauss supposedly did it as a child. But if I really want to prove this, I should write an inductive proof. Exactly the way we just did up above. So in spite of having a pattern isn't a proof. It's a hunch. And I don't like building my worldview off of hunches. We will, in the calc class, eventually show that there is a nice formula, not just for the pattern where you add up the numbers, but a pattern where you add up the squares, and a pattern where you add up the cubes. And as a matter of fact, there's a pattern for any power that you want to add up. These get more and more complicated as we go along, but I'm going to use these in about a week and a half in Calc 1. More questions? We matched to make a pattern here, right? This is what we just proved, right? You ready for the pattern? One plus 3 plus 5 helps if I put them lined up. Plus 7. See the pattern going on? I always end up with a square, don't I? Well, if I always end up with a square, that should still be a square, shouldn't it? No matter how many pieces I have. That's the next odd number, isn't it? 2n plus 1. 2n minus 1 total. There we go. But a pattern is a great desire to see that something's true. It doesn't actually show me that it's true. The actual argument here does. Questions? There are a lot of images like this that label themselves as proof without words. No, it's a hunch. You know what the other side of this pattern is? Wait a minute, I asked you to convert 1023 to binary. In the homework, and you got 1. You add 1 to it, when all those bits roll over. 1. Yeah, those are all, that's N ones in a row, isn't it? It's a great hunch. Let's prove it. Well, a direct proof is unfortunately not going to work. I'm going to prove this inductively. What's your base case?
Zero.
It would be 0. Pick the smallest value of n, see if it works when n is 0. Well, if it's 0, on the left-hand side, my value of n is 0. 2 to the 0th is just 1. On my right-hand side, n is 0. So I get 2 to the 0 plus 1 minus 1. That's equal 2 to the first minus 1. That's just 2 minus 1. Hey, those are equal, aren't they? The inductive case always starts with an induction hypothesis. What is my induction hypothesis? Suppose what?
You got P of n implies P of n plus 1, where P of n is defined as that sequence being equal to 2 to n plus 1 minus 1.
Yeah, but that's what I'm trying to show overall, right? So I don't think I want to use n again as my particular issue. So I'm just going to use k. But I start with P of k, right? Suppose that 1 plus 2 plus 2 squared plus 2 cubed plus up to 2 to the k is equal to 2 to the k plus 1 minus 1. I didn't even write it out as P of k. I just wrote the whole sentence, said we're going to stop at k instead of n. Right? Now, I want to show, WTS is just an abbreviation for that. I want to show that the pattern holds for one more. I want to show that I can get from P of k to P of k plus 1. So I start with the left-hand side. And I say to myself, how can I use the hypothesis part here?
And then everything minus the 2 to the k plus 1, that's all equal to 2 to the k plus 1 minus 1.
That's helpful. How is that helpful?
you can simplify it to being 2 times 2 to the k plus 1 minus 1.
I rearrange. Though that's two of the same thing. So it's two of them. Wait a minute, I got 2 times a power of 2. What do I do with the powers?
Just add 1 because it's 2 to the 1 times 2 to the k plus 1. And the rule is you can add the next thing.
And that's where I wanted to be, isn't it?
Sorry, can you show more work with that? I'm kind of confused.
Sure.
with that.
We'll go from this line. We'll write that as 2 to the k plus 1 plus 2 to the k plus 1 minus 1. I'll just switch the sides. So this is 2 of 2 to the k plus 1's minus 1. Oh, but 2 of something, that's 2 to the first times 2 to the k plus 1. Well, now those are both powers of 2. When you have power of x times power of x squared times x squared, what do you do with the powers? So I just added these two numbers. 1 plus k plus 1. But that is exactly where I wanted to end up. And there's my conclusion. The statement I wanted to show to be true is true for all values of n bigger than or equal to 0. The general idea is the same for every proof by induction. My goal, always, find a base, show that it's true. Write the inductive hypothesis, and use that to prove the next one in line. Show I can knock down some domino, and then show that each domino knocks over the next one. The reason this works is something called the well-ordering principle of the integers, which is a really deep topic in the analysis and set theory courses, and we're not going to discuss the why behind it. There are a couple of paragraphs about that in the book. Questions?
Does that mean you have to have the base case be as small as possible? Like if we chose n to be 2, for example.
Then I would only have proved it from 2 on.
Yeah, so that wouldn't work.
That would work absolutely. But what about 0? What about 1? I can pick any base case I want.
That's what I'm, yeah.
Yeah.
If I was trying to prove 0 to up and I am the 2, that means the proof is invalid.
Well, it's incomplete.
Yeah.
Now, the one we did to start with, right, with the squares, I had base cases that were true up to 5 already written out, didn't I? So I could have started at 5 because I'd written out the base cases already. Yes? There's no reason not to say, hey, let k be a number bigger than or equal to 6. And then I would show it from 1 on. Because I worked out the base cases manually.
Is there any way to go in the reverse order? If you wanted to start with a max and go down?
Only if my goal is to go to minus infinity. So yes, but that's because the induction property, the well-ordering principle, works in both directions. Very, very, very rarely will we work a case down. But this idea can be turned on its head exactly like that. Hey, in order to know this one, I have to know this one. In order to know this one, I have to know this one, and this one, and this one, and then I hit a bottom, right? Isn't that the definition of a recursive behavior? Guess why recursive algorithms work? Because we have a base. If your recursion doesn't have a bottom, you'll fail, right? Your loop will never terminate recursing downward. This is the exact reason we can do recursion in any algorithm at all. Because I can show a base. And I have to show that one manually. Even if in your recursive argument you go, oh, well, the original was just 1. Now let's build back up. On, I believe it's page 341, there's a very interesting example, in my opinion, about a series that we may or may not have talked about here, but I know we will talk about in calculus. It's called the harmonic series. And the harmonic series is actually an infinite series. It goes on forever. Now, there are some series of numbers that you can add up, infinite many things, and still get a finite number. We did one. Back in chapter 2, we did this. And when we added that all up, we got 1. Now, again, I didn't actually prove it. I wrote out a picture, cutting the half of the square and then the half that was left over and so on. And I said, eventually we'll just run out of square. What happens when I go to add this up? Well, I keep adding smaller and smaller things, right? Here's the problem. This never stops growing. This total actually goes off to infinity. Really, really, really slowly. If you want to add up and get a total bigger than 50, you need to add up over 2 trillion numbers. You've only reached 50. But we can actually show recursively that this will never have a finite total. And that argument appears here on page 342 in example 7. So induction works in lots of different places. It doesn't just work on sequences of numbers, in spite of the fact that that happens to be where I'm using it at the moment. It works in a lot of other settings. It works on series, it works on matrices, it works on algorithms. It works in a lot of different options. But sometimes the induction idea isn't quite enough to do what we want. And it comes from our induction hypothesis. We only know about the one right before. We're wanting to prove something about k plus 1, we only know something about k. Right. Because when we did stuff like prime factoring, we didn't know about the previous number. We had to say, oh, there's some number down there that may or may not divide, right? I should start checking. I started with 2, and I worked my way up until I found 1, right? So in some cases, there's another induction idea. Principle of strong induction changes one thing. It changes our induction hypothesis. Instead of, hey, just suppose the one before was true, I want to suppose that all of the ones before were true. So I'm not just using one domino to knock down the next one. I'm using all the dominoes that came before to knock down the next one. I don't know what number should go on the left. Whatever number is our base case is going to go on the left, but that could be 0, 1, 2, 7, whatever it is. But I don't want to just show that one of them before is true. I want to suppose all of them are true. Now you may ask, why the hell would you need to do this? We used this when we talked about prime factoring. And I said, you can always prime factor a number. And you all just went, okay. How do you know I'm not lying my ass off? Because it worked every time we did it. That's not a proof. That's a hunch. So I start saying to myself, I'm going to prove this. And I say, I'm going to try and prove this by induction. Well, my base case will be 2. Is 2 a product of primes? Yeah, because 2 itself is prime, and a single value is enough. Check. Suppose a number k is prime. Suppose 7 is prime. How are you going to use the fact that 7 is prime to tell you something about 8? Suppose I have a number and I know I can write it as a product of primes. 8. 8 is 2 times 2 times 2. How does knowing that tell you how to figure out what to do with 9? Doesn't tell me shit, does it? I'm not reaching far enough back. If we have a number that is not prime, then it has to have a factor. And all I know about that factor is it's less than the square root of the number. Not 1 less than the number, it's less than the square root of the number. It's way further back. So instead of just going 1 step back, I need to go much further back. That one's easy. Notice how different my hypothesis is. It's not just, hey, 1 back is good enough, but all the numbers back. All the way back to 2. Now we look at k plus 1. What is my eventual thing to show? What do I want to show here?
A plus 1 is the product of primes.
So I look at this number. If it's prime, I'm done. I have a case. Case 1. K plus 1 is prime. I'm done. What's case 2? It's not prime. That means what? That means that K plus 1 can be written as A times B. I know nothing about A or B, except I know a little bit more than that.
Square root A plus 1.
I know a little bit more than that. I don't know that yet. 100 is 10 times 10, and neither of those are prime. I know they're not 1, and they're not K plus 1. Primes are only divisible by 1 in themselves. Non-primes have to be divisible by other things. Wait a minute. If A is strictly bigger than 1 and strictly smaller than K plus 1, then that means it's bigger than or equal to 2 and less than or equal to K, isn't it? Where have I seen that before? That's my hypothesis. I don't know if A is prime, but I do know that A can be written as a product of primes. For the exact same reason, so is B, right? What does that mean about K plus 1? K plus 1 is A times B, product of primes, more product of primes. Isn't that a giant product of primes? But I wasn't just going one step back. I had to go further. There are a lot of these that are rigged. You are only allowed to pay for your meal in bills, dollar bills, $5 bills. Can you pay for a meal of any amount of dollars? Well, sure I can. I can pay for 1, 2, 3, 4, and 5, right? I only can use $1 bills and $5 bills. I can pay for 1 through 5. $1 bills up to 4, and then $1 $5. Pick any other number. 382. Take as many 5s out of it as you can, and then pay with what's left with $1 bills. That sounds like recursion, doesn't it? It's our cashier's algorithm. But it's an inductive behavior. I could do 2 more weeks on induction and recursion. I'm not going to. I'm going to leave that for the algorithms class. But again, the rest of chapter 5 does things like heap sort and merge sort, which are recursively designed algorithms. And it shows you how to calculate the big O of these things. So you can put all of these together. I will be talking about a new topic on Friday. I will see you all then. If you came in late and have homework for me, please bring it up. Please note that the assignment for this chapter includes a couple problems from 5.1 and a couple problems from 5.2. They're together.